smarter tricks to do it, but let's first see what we do. We first define the variable omega squared, which actually we call omega 2, which we set equal to 1. Then we define a function which takes arguments y and t. The underscore is really a pattern, which really means an argument, which returns a list where the first element is the second element of the list y, and the second element is minus omega squared times the first element of the list y. That's the way to actually realize if the first element of y is actually the position x, and the second element is actually the velocity v, then this has the derivative of x is v, which is clearly correct, and the derivative of v is minus omega squared times x, which is indeed Hooke's law, nothing else, for a particle of mass 1. Then the next thing we do, we define the RK4 method, which again takes y as an input, t, the riff, which will actually be the function, and a step size h. And it has local variables k1, k2, k3, and k4. We define k1 is h times the derivative, k2, k3, and k4, exactly like we've done before, and then we multiply everything together to get the new y and the new t, which are, since they are the last thing in the function, are actually the numbers returned by the function. Then the next thing we do, we define the energy. We take an energy of 1 in this case. We take the starting position x naught is equal to 1. We take h is 0.01, and that's perfectly a sensible thing to do. Then we start at time 0. We define y, which is our vector, which is x naught, and we actually use the energy expression to find one of the two allowed values of the velocity. We choose the positive one in this case, and then what we do, we actually make a table of solutions for 2000 values of the argument, where each time we define the new y of t as essentially the one step of RK4 based on the old value, and then of course in order to make it sensible we need to plot it. I do some jiggery pokery over here. This just extracts the first element to any of the list of the solutions, and if you look very carefully, the first element is actually nothing more than the combination x and d by dx, because it's a list, and so we make the list line plot of that, and what we get is a very nice, lovely picture of a circle, which clearly the orbit in phase space, which this is what we expect it to be. We could have, of course, also plotted position and velocity separately. There's a trick for that as well. We hash 2, which means the second element of the list extracted should work, and then essentially if we work our way through this, then this should exactly give us the right answer. And indeed we can clearly see that the plot we have, we find that x and t are the standard out of phase behavior, right? I mean, if x is maximum, the velocity is 0, and if the velocity is maximum, x is 0, which is exactly what we expect.